S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult concepts made easy. Study anywhere, anytime.
Do you know a function can be expressed in terms of a series? So to understand this topic, in this lecture we will be studying Taylor's theorem and Mclaren's theorem. Hello everyone, I am Dr. Seema Dhakran. So let's start with Taylor's theorem and Mclaren's theorem. Both the theorems have two forms, and I will be expressing a function in terms of a series. So let's learn how to do that. If you want to study this topic in detail, please refer to the book by S. Chan Publishing. The e-book link is given in the description box. So first I will be writing the statement of the theorem, then we will be taking few examples based on the theorems and how this theorem is useful whenever, like, we know sin theta lies between -1 and 1, but how you calculate that it is lying between -1 and 1. So this theorem, these two theorems will be helping how to basically get the upper bound and lower bound for the particular functions, fundamental functions. So fundamental functions we have already studied, like sin x, cos x, e to the power x, that is exponential. So let's start with the statement of the theorem. Taylor's theorem. I will start with theorem statement. In our last lecture, that was lecture 11, we studied Lagrange mean value theorem. So Lagrange mean value theorem is particular case of Taylor's theorem. How come? So after the statement I will be just briefing you. So we can say this theorem is generalized mean value theorem. In short, I will be writing mean value theorem. So this is generalized mean value theorems. So statement I have written, and the statement is, let fx be a function on the closed interval a to a plus h. Though two conditions the function should satisfy, it means, and the conditions are fn minus 1 derivatives are continuous in a closed interval a to a plus h, and fn exists for all x in open interval a to a plus h. If this is the case, then there exists a theta lying between 0 and 1 open interval such that f of a plus h equal to fa plus hf dash a plus h square by 2 factorial f double dash a plus and so on plus hn n factorial fn a plus theta h. So this is how you can express any function if these two conditions are set, the function is satisfying. This expression I will write in a way in which the convenient way I will be writing. This is the standard form, but the most standard form I am just writing. And what exactly that standard form is? That standard form is, put h is equal to x minus, it's just the reframing the equation only, nothing else. So what exactly you will get? That will be fx, fa plus x f dash a plus, x minus a, because h is, I am replacing by x minus a. This will be x minus a whole square upon 2 factorial f double dash. You can see, if this power is 2, derivative is also second derivative. If this power is 1, derivative is first derivative. So with the power you can see the derivative, you can match both the power and the derivative. So this is the form. Most commonly used form is this one. So this is more convenient if you are doing any question. Now this is the last part, this one. You just see this part. This is the remainder part, we call it Rn. So if the remainder is of this form, we say this is Taylor's theorem Lagrange form of remainder. Lagrange form of remainder. Now in this form, just simply put up x a0, just simply put a equal to 0, the point you will be putting as a0, your form will look like fx equal to f0 plus x f dash 0 plus x square by 2 factorial f double dash 0 and so on. The last remainder term, which is important, it will be xn upon n factorial fn a. This is 0, so simply theta x. This form you will be remembering, because using this form only will be just evaluating or approximate the function. How come? We will understand through the illustrations. So this is the form. Now why I have put 0? This form is Mclaren's. This is Mclaren's theorem, because whenever you will put the point 0, that will be the Mclaren theorem, and the remainder form is same. So Mclaren theorem, Lagrange form of remainder. Form of remainder. So two theorems we did. One is when we substituted the point 0. In another we have the point as, you can see, this is the form and then another form is this. Whichever form you find convenient you can use. We have another standard form also, and that is this one. So it's totally up to the student which form he or she is just finding convenient. So Mclaren form of Mclaren theorem, Lagrange form of remainder we did, and then Taylor's theorem, Lagrange form of remainder we have done. This is basically called the remainder. Now I will just start with Taylor's theorem, Cauchy's form of remainder. Another form. So Taylor's theorem, Cauchy's form of remainder. What exactly it is? Let's start with the statement. Let fx be a function. Conditions are same in closed interval a to a plus h. Again, also let fn minus 1 derivatives are continuous in closed interval a to a plus h. Fn exists, it means the nth derivative exists for all x in open interval a to a plus h. If this is the case, then there exists a number theta lying between, this is for between BTW, open interval 0, 1. If this is so, the form will be f of a plus h, f a h f dash a plus h square by 2 factorial f double dash a and so on. The last is the remainder point where there is a change, and what exactly that remainder is in this case, this is the remainder in this case. So this is the change you will be just observing. So the last term you can see, this term is important, you can see the difference. This is Rn, the remainder, and this is the Cauchy's form of remainder. So this is the difference in both the forms. So this is Taylor's theorem in Cauchy's, C-A-U-H-Y, C-A-U-C-H-Y, Cauchy's form of remainder. Anyhow, the first one is most common, which we use. Again, what you do, just substitute h equal to x minus a. If you find this form convenient, then what will happen? The expression or this equation will become fx equal to fa, x minus a f dash a, then x minus a whole square upon 2 factorial f double dash a and so on, plus x minus a whole power n upon n minus 1 factorial 1 minus theta to the power n minus 1 fn a plus theta and h is x minus a. Again, if this is the form, whichever form you find convenient you can use, but this is most common. So, I will suggest you whenever you do a question you should be using this form. Now, I am just substituting a0 because this is Taylor's form. If your a is non-zero, this is Taylor's form, Taylor's theorem, but in case your point is 0, a is 0, that particular case is Mclaren's theorem. So, when you will substitute a0, your form will look like f0 plus x f dash a plus x square upon 2 factorial f double dash 0 because a is everywhere 0, then xn upon n minus 1 factorial 1 minus theta to the power n minus 1 fn theta x because a is 0. So, this is, if a is 0, this is Mclaren theorem, Cauchy's form of remainder. So, in all I have given you 6 forms, Taylor's theorem and Mclaren's theorem. Just learn all the forms to get some to do the evaluations. So, after the break we will be taking the illustrations.
Hi, I am Manika and you are watching Chand Academy. I will be discussing the topics like carbohydrates, amino acids, peptides, proteins and many other topics related to BSc program. For more such lecture, you can stay tuned to our channel and subscribe to our videos so that you get more and more info about our upcoming lectures. You can also refer to our previous lectures on the related topics. Stay tuned, stay focused because it may help you in your competitive exams also and preparation of the other topics also related to your courses. Thank you.
Welcome back to Chand Academy. Before going to the break, I just told you to go through the 6 forms which I gave you before the break. Now, I have already written one question on the board. So, you can see the question is verify Taylor's theorem for fx equal to 1 minus x to the power 5 by 2 with the Lagrange form of remainder up to 2 terms. So, it is not that every time you will be getting it for n terms. So, it is up to 2 terms in the interval 0 to 1. Interval is 0 to 1. How to start with the problem? You have to verify it, means the theorem which I stated before the break, you should be checking whether it is correct or not, the statement. So, how to verify? So, start with the solution. So, solution. What exactly your function is? So, we have everything is based on the function. See the function first. Our function is 1 minus x to the power 5 by 2. If it is up to 2, it means according to the statement of the theorem, first derivative which is power rule you apply for the derivative, differentiation also we have already done. So, 5 by 2, 1 minus x to the power minus 3 by 2, because what you do, power in front and you just subtract 1 from the power. So, what it will be giving you, plus it will be, and derivative of the expression it is minus 1. So, finally, your first derivative is this one. You will be checking the continuity, there is no issue, this is algebraic function. So, the function this first derivative is continuous, no issues at all in closed interval 0 to 1. Coming to second derivative now. So, what will be the second derivative? Same technique you apply to take the derivative. So, it is minus 5 by 2 and 3 by 2 in front, then just again reduce 1 from power, and derivative of this minus x derivative is minus 1. So, it will become plus 1. So, this is the derivative, just simplify it. So, your derivative ultimately is this one. You can see this is completely a differentiable function, there is no issue at all at any point with in the interval 0 to 1. So, it exists, you can say. So, second derivative exists, no issue at all in the open interval. It means if it was for second order derivative should exist and first order derivative should be continuous. Both the conditions are satisfying, but it is not that the Taylor theorem is got verified. So, for the theorem, what to do? Now, first derivative we have checked, second derivative we have checked. Come to the Taylor's theorem. What exactly the statement or the form of the Taylor's theorem for up to 2 order? How? So, Taylor's theorem, Lagrange form of remainder, which is said in the question. Lagrange form of remainder. It is not up to n terms. So, what was the form? Fx f0 plus x f dash 0 plus x square by, this is up to 2 means you will be just stopping your expression to power 2 and second derivative theta x we write. So, this is the theorem up to 2 degree. So, this is the statement, and now what exactly your theta lying between? It is lying between 0 and 1. So, ultimately what will be checking, verify कर रहे हैं हम लोग. So, verification के लिए theta की value 0 और 1 के बीच में अगर आई तो we will say कि it is verifying and it should verify anyhow. So, let's start. With this expression only we will be finding the theta value. So, put up all the values which we have, first derivative we have. So, fx is, my fx is 1 minus x to the power 5 by 2 equal f, okay, my fx is, I just write it here. What will be f0? x0, this will become 0, so it means f0 will be, so f0 is simply 1 plus x, f dash was how much? It was minus 5 by 2, 1 minus x to the power 3 by 2. When you are substituting 0 here, your f dash 0 will be minus 5 by 2 plus x square by 2 factorial. Then f, second derivative was 15, 5 3 is 15, 4, 1 minus x to the power half, put x equal to 0. So, when you are substituting this, f theta x, so this will give you 15 by 4, 1 minus theta x to the power half. So, this was the form when we put a0, and now what you do? This is, I told you, one of the important form, because this form only will help you to verify. Now come to put x equal to 1, because we just want only theta and x basically lying between 0 and 1. What you do? Put x equal to 1, this side it will give you 0, because we are just verifying whether theta is satisfying or not. 1 means this will give you minus 5 by 2. Then this again, this will be 15 by 8, 1 minus theta to the power half. Just simplify it and just check whether this expression, the value we are getting the value of the theta which we are getting from this expression, if it is lying between 0 and 1, our purpose will get solved. Just simplify it. So, what it will give you? This will give you minus 3 by 2 plus 15 by 8, 1 minus theta to the power half. Take this to this side. So, what it will become positive. This is in multiplication. So, it will just come in this side and it will get reversed. So, finally 12 by 15, 1 minus, just square both sides. Squaring on both sides will give you 144, 225, 1 minus theta. This implies take theta to this side and this expression to that side. It will give you finally this. So, 225 minus 144. So, 81 upon 225 sorry, and if you will just calculate it, this is 0.36 and it is very clear that it is lying between 0 and 1. So, it means the Taylor theorem verified is verified. So, I just brief you the question again. It was up to 2 order. So, it means first order should be first derivative should be continuous. Second order derivative should exist. If this is the case, then theta, a number lying between 0 and 1, this form is more convenient. So, you will be just keeping this form if you are solving any or doing any verification. In this form, first a0 we have kept, then x1, because any value between 0 and 1, this theta should get satisfied, and finally we are getting theta as 0.36. So, we have seen how to verify the theorem. We have done one question. Let us start with the second illustration, and that is if your function is log of 1 plus x, where x is greater than 0, Mclaren's theorem, using Mclaren's theorem, show that theta lying between 0 and 1, your log of 1 plus x can be written as x minus x square by 2 plus x cube by 3, 1 plus theta x whole power 3. You can see 1 plus theta x and it is up to the power 3. It means now in this case we will be just writing the theorem up to 3 order. Up to 3 order means third derivative should exist. Till second order the function should be continuous. So, let us see whether the function log 1 plus x satisfying the theorem or not. So, solution. So, we have fx equal to log of 1 plus x. First, what to do? Because we need derivatives, first take derivatives first. So, log derivative is 1 plus x in the denominator, 1 plus x derivative will be 1 only. Now, take up the second derivative. Second derivative will be minus 1 upon 1 plus x square, as because this is linear function na. So, 1 upon x derivative we write as minus 1 upon x square, same way I have written, no need to be using the quotient formula. Now, third derivative. Third derivative will be 1 upon minus 1 upon x square derivative, that is 1. Quotient rule you can apply, or simply this is somehow standard formula. So, you can apply it directly, 2 upon 1 plus x whole cube, quotient rule. Now, these are the derivatives, okay. You can see easily your x is greater than 0, your x is greater than 0. So, it means there is no issue, your first derivative, second derivative continues because x is greater than 0. So, there is no point where these two functions, the derivatives can create problem. So, I am just the f2 derivatives are continuous, first condition got satisfied, are continuous because there is no point where the function is having any issues in closed interval 0, 1. Then the third derivative is existing, you can see exists in open interval 0, 1. Now, what is the form for till third order? Till second order we have already written. The same way write the theorem for third order. So, Mclaren theorem, Lagrange form of form of remainder up to 3 order. Up to 3 order, what it will be? Fx f0 plus x f dash 0 plus x square by 2 factorial f double dash 0. This time one more term will be adding because it is still third order. This is the remainder, so theta x will be writing because this is the remainder, that is the important part. Now, fx is log of 1 plus x. What is f0? Your fx is log 1 plus x. This is your fx. When you are substituting x0, log 1 value is 0. So, this is completely 0. Now, what is f dash 0? I have already written the first derivative was 1 upon 1 plus x. Substitute 0. So, it is giving you 1. Then coming to second derivative, what it was? It was minus 1 upon 1 plus x whole square. Substitute here also, so it will give you minus 1. And now the last derivative, third derivative. What was third derivative? It was 2 upon 1 plus x whole cube. So, instead of theta, you will be putting theta x. So, what it will give you? 2 upon 1 plus theta x whole cube. Okay. Now, just simplify. When you will simplify, you can see if everything is just correct, you can see it should give you exactly what you basically need to prove. So, this is 3 factorial, only I will just open this 3 factorial, this is 3 into 2 into 1, this is how we open, 2 gets cancelled, and this is what we were supposed to prove, you can see. So, finally we got log of 1 plus x as x minus x square by 2 factorial plus 2 factorial is 2 only. So, we can say it is this way also we can write. So, x minus x square upon 2 plus x cube upon 3 1 plus theta x whole cube. Now, there is another requirement also that log of 1 plus x is less than some expression. So, how to now move to that point? So, we have the expression which you have now, log of 1 plus x less than something, okay, less than something, and this term is not there. This term is not there, it means my focus should be on this term only. Anyhow, I just get this term removed, and how I will be just removing it, just see. So, we have x greater than 0 and your theta is lying between 0 and 1. Okay, so it means theta is also greater than 0. It means theta x greater than 0. Both numbers are positive, so multiplication will also be positive. Then, according to this expression, 1 plus theta x, obviously you are adding 1 only. So, this will again be positive. Then, if a number is positive, whole cube also be positive. There is no chance that the cube will become negative. Okay. Now, 1 upon, if this number is greater than 0, then 1 upon 1 plus x whole cube, because now you are taking in denominator, this will be less than 1. This is for sure. Any number 2 is greater than 0, then 1 by 200% will be less than 1. So, it means from this step onwards, this is the last step now. So, we have log of 1 plus x as x minus x square by 2 plus x cube. This is what we have already got. And because of this thing, 1 upon this is less than 1. So, it means this whole expression will become less than. So, this was our requirement. We have already solved this. So, we used, you can see log of 1 plus x is less than this. It means this is upper bound for the function log of 1 plus x. So, to get upper bounds, lower bounds, we can use these theorems, and this is all about this lecture. So, in this lecture, we studied Taylor's theorem, Lagrange form of remainder, Cauchy's form of remainder, then Mclaren's theorem, Lagrange form of remainder, Cauchy's form of remainder. If you want to study this topic in detail, please refer to the book by S. Chand Publishing. The ebook link is given in the description box. Don't forget to share, like and subscribe the S. Chand Academy. Don't forget to press the bell icon for the future updates. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.